Hello everyone, welcome to Energy Conversion 2 class. We are doing with chapter 3, that is synchronous motor, and today's topic for discussion is power flow and different torques in a synchronous motor. So coming to the power flow within a synchronous motor, let Ra is the armature resistance per phase, Xs is the synchronous reactance per phase of the synchronous motor. Then Zs, the synchronous impedance will be Ra plus Jxs, or we can also derive Ia is nothing but the resultant voltage or EMF divided by the synchronous impedance, or we can say the difference between the supply voltage and back EMF divided by synchronous impedance. Obviously, for this synchronous motor, supply voltage V equals EB plus Ia into Zs. Here we can see the phasor diagram. This is the supply voltage, armature current, this is the back EMF, and this is the resultant EMF. The resultant of back EMF EB and supply voltage V. And here is the IAZ. This is the theta angle, the angle between resultant EMF and current. This is the phi, phase angle, the angle between voltage and current. The angle theta is also known as the internal angle. We have already seen, by which Ia lags behind ER is given by tan theta equals Xs by Ra. Remember the formulas. If Ra is negligible, then theta equals 90 degree, motor input equals V into Ia into cos phi per phase. Here V is the applied voltage per phase. Here we can see the total input for a stator connected motor 3-phase machine, that is P equals √3 VL IL cos phi. The mechanical power developed in the rotor is Pm equal back EMF into armature current into cosine of the angle between the two, that is angle between Ia and Ev. You can see Eb into Ia into cos alpha minus phi per phase. Now power flow within a synchronous motor. Out of the power developed, some would go to meet iron and friction and excitation losses. Hence, the power available at the shaft would be less than the developed power by this amount. Out of the input power per phase, that is Vi into cos phi, and amount Ia square Ra is wasted as loss in the armature. So the rest, that is V into Ia cos phi minus Ia square Ra, appears as mechanical power in the rotor. Out of it, iron, friction and excitation losses are met, and the rest is available at the shaft if power input per phase of the motor is P. Then P equals Pm plus Ia square Ra, or mechanical power in the rotor will be Pm equals P minus Ia square Ra per phase. So for 3 different phases, as we are dealing with 3-phase machines, the Pm will be √3 VL IL cos phi minus 3 into Ia square Ra. Here we can see the power flow diagram. This is the power input per phase in the stator, P V into I into cos phi, and here there are 2 powers, armature copper loss. For this same power, 2 losses can appear. One is armature copper loss, another is mechanical power in the armature. So after finding out the losses, Pm formula becomes Eb Ia cos alpha minus phi. Now there are also another laws, iron, friction and excitation laws. So now the output power is P out. Here you can see AC electrical power input to the stator, that is P in. Here is the stator copper loss. Here are the mechanical power developed in the motor, PM. Again we have iron, friction and excitation losses, and after subtracting these losses we will get the total output power at the shaft of the synchronous motor, that is P out. Here we will see different torques of a synchronous motor. So various torques associated with a synchronous motor as follows. First one is starting torque, then comes running torque, third one is pull in torque, and the fourth one is pull out torque. First one is your starting torque. It is the torque, or we can say the turning effort. Due to this only the motor turns, the motor rotates. So it is the torque developed by the motor when full voltage is applied to the stator or the armature winding. And let me tell you, it is also sometimes called the breakaway torque. The starting torque is also known as the breakaway torque. Its value may be as low as 10% as in case of centrifugal pumps, and high as 200 to 250% of full load torque as in case of loaded reciprocating two-cylinder compressors. So remember, these can be the variations in the torque, or we can say starting torque values. Next, second one is your running torque. As its name indicates, it is the torque developed by the motor under running condition, that is under normal operating conditions. The torque developed by the motor is known as the running torque, and be clear, it is determined by the horsepower and speed of the driven machine. The peak horsepower determines the maximum torque that would be required by the driven machine, and the motor must have a breakdown or maximum running torque greater than its value in order to avoid stalling. So the running torque is nothing but the normal operating torque. And also note this point, the motor must have a breakdown or a maximum running torque greater than its value in order to avoid stalling, in order to avoid the maximum running conditions. So now third one is your pull-in torque. A synchronous motor is started as induction motor till it runs 2 to 5% below the synchronous speed. So afterwards excitation is switched on and the rotor pulls into step with the synchronously rotating stator field, or we can say the amount of torque at which the motor will pull into step is called the pull-in torque. Next one is your pull-out torque. The maximum torque which the motor can develop without pulling out of step or without losing its synchronism is called the pull-out torque. Normally, when load on the motor is increased, its rotor progressively tends to fall back in phase by some angle called load angle behind the synchronously revolving stator magnetic field, though it keeps running synchronously. The motor develops maximum torque when its rotor is retarded by an angle of 90 degree, or in other words we can say it has shifted backward by a distance equal to half the distance between the adjacent poles. Any further increase in the load will cause the motor to pull out of the step, or it may be out of the synchronism, or we can say it may simply stop. Thank you.